All right, so what I'm gonna do is set up a couple pieces of regular old tape, Scotch tape, and there's a process that you can go through to actually make them carry a different charge, okay? So we're gonna have something called a T tape, which I'll kind of attach here, and a B tape. T is just for top tape, B is for bottom tape, and they should behave differently depending on whether they're a top tape or a bottom tape. So that you can kind of see how I set that up, I'm gonna turn on my camera here. And so what I do first, I take a nice long piece of tape, and this is just gonna go on the table, straight on the table. And this is not going to be a B tape or a T tape, this is just what we call the base tape. And it stays put, it will stay on the table. And just make sure that's kind of fixed to the table nice and tight. There. Let me turn off the light here. Okay, that's better. All right, so my next tape is going to be my B tape, meaning bottom. And I fold it over just to give myself a non-sticky handle that I can pick up. And that's gonna go right on top of the base tape. Label it with a B. So I know which one is which. And then next is going to be the T tape, T for top. Again, I just make a little handle so I can pick it up without sticking to it. Tape. Now to get them to carry a different charge, you peel them both off together. So I've got the B and the T tape. You touch the top of the T tape and then you pull them apart. And they should now actually be carrying a different charge. So I'm going to stick the B tape here by the B, the T tape by the T. Ooh, see what they wanted to do already. They start to have a life of their own when you do that. Okay. Now I will say that this works best when a room is very dry. Okay, so it works best like if the heaters are running. We have a little bit of humidity in the air, and these charged pieces of tape, the charge kind of leaks away when you have a lot of humidity in the air because of the water vapor in the air. So I'm hoping this works well. It wasn't great first period, but I'm hoping that it'll be better this period. So if I struggle a little bit and have to like reset the tapes, that's why. So what I want to do first is kind of look at our observations here in the upper left corner of the handout. And on table is going to be the ones that are here set up on the table. So we have a T tape and a B tape that are on the table. And I want to bring them together with a B tape and a T tape in my hand and observe what happens. So I need to set up another set of tapes, a new B tape. B, and T. And all we really know right now is that they're going to have a different charge. We don't know, is it positive, is it negative? That's what we're going to try to figure out. All right, so again, I lift them both off the base, I touch the top tape, and I tear them apart. So this is the T tape in my hand. What I want to do is bring that to the other T tape and the B tape. I want to get their non-sticky sides together. Whoops. Okay. So T tape to T tape. Oh, it's actually working quite well. You see that? It's pushing the T-tape away. We're gonna call that repel. So T to T is repel. T to B is attract. So bring this T-tape to the B-tape, T in hand, B on table, they attract. All right, I'm encouraged by that. It did not work that well first period. So T to T was repel, T to B was attract. All right, now I've got the B-tape in my hand. It's stuck to me. Let's go B-tape to T-tape. It's an attract. So B in hand to T-tape on table is attract. And then let's do B to B. Can you see that it is pushing away? It's not as strong, but when they get together, they push apart, so that's going to be a repel. Again, B to T is definitely an attract. I'm trying to bring them together, and it definitely pushes apart. Okay, now the trick is, I kind of reset these. All right, so summarizing, T to T, we saw repel. T to B, we saw attract. B to T was also attract. And B to B was repel. All right, I also want to check out a couple of other materials. I want to look at aluminum foil. So I have some aluminum foil strips and some paper strips. I'm going to attach these over here on the other setup. And I'd like to see how the B and T tapes affect those. So we've got paper. So I reset my B and T tapes over here. All right, so I'll take my T tape along the top row here. Let's see what happens if I bring the T-tape towards the foil. There is an attraction there. They come together. Okay. T-tape to paper. It also attracted. You got to get them a little closer together before they attract. But there is an attraction with the paper as well. I think I can get the foil to attract a little bit further distance away. So those are actually both going to be attract and attract. So what do you think the B tape's going to do? Let's go B tape to foil. It attracts. That might be a surprise. B to foil attracts. And B to paper attracts. So it didn't matter, T-tape or B-tape, both of them attract the foil and the paper. So the T-tape attracted both. would say usually it wasn't a super big difference this time, but I tend to see that the paper attraction tends to be a little bit weaker. I'm gonna call it a weak attract. When the conditions are really good, the foil really attracts quite strongly. So we had an attract, and again, I'm gonna say a weaker attract. For the paper. Alright, so next, just to make sure that it doesn't matter whether the foil and paper are on the table or in my hand, I want to bring the paper, a piece of paper and a piece of foil in my hand to the T-tape and the B-tape here. And those may have lost their charge, but we'll see. We'll see. I'll start with foil. So this would be bringing foil near the T-tape. And like I said, it may need to be recharged. Oh, it's gonna attract. So foil to T-tape attracts. Foil to B-tape also attracts. And I think probably to some degree the charge is weakened a little bit here, but we definitely did see an attract. So attract and attract. And then I want to bring the foil over to another piece of foil and paper, see if we get anything there. If there's something there, it's not much, right? I can bring it right close and it is not attracting. So let's just put an X there. It appears that foil to itself does nothing. It neither attracts nor repels. And foil to paper, I got nothing. Yep, nothing. So that's interesting, right? The foil interacts with the tapes. It does not interact with itself or paper. Let's try paper. All right, so paper's in my hand. Paper to T-tape. Weak attract, I would say. If I get it close, they cling together. Paper to B-tape. Again, I would say it's another weak attract. Again, I just want to check paper against foil, paper against itself when I have paper in my hand. Nothing. Big X. Paper to paper, that final piece. Nothing. So by themselves, the paper and foil don't really do anything, but they always attract if they're brought to a T-tape or a B-tape. Okay. So we want to just kind of get some summarizing rules about how they interact. Let's focus on the T's and B's first. Right? The repel always happened when we had the like types of tape, okay? Whether it was T with T or B with B. So we can make a rule that says like tapes repel. we talk about charges, we usually talk about like charges or opposite charges. Opposite meaning different. We can use either word here. The different tapes, so T to B attracted and B to T attracted. So let's say different tapes. And then let's talk about foil. Okay, foil attracted with either tape, but did not attract itself or paper. Okay, so let's say foil attracts B, let's say B and T. And paper did the same, maybe somewhat more weakly. Paper attracts B and T, maybe somewhat more weakly. And then finally, paper and foil alone do nothing, right? There's no attraction, there's no repel. So for our clearly charged things, we could say like charges repel, different charges attract. We're going to have to do some more thinking about what's going on with the foil and the paper, because sometimes they attract when we're dealing with the charged thing, but to themselves they do nothing. So that's a little bit mysterious at this point. Right? Questions up to that point? All right, so let's flip over to the back. Part 2 says we want to see if we can assign charges to the B and T tape. Okay? So it says, after you've summarized your findings, attraction, repulsion, no interaction for the two tapes, foil and paper, rub a hard plastic or hard rubber rod with fur or wool, okay? This is a process that kind of like with the tapes when I separated them, can cause a charge to form, okay? So I'm gonna approach the T tape, the B tape, the foil, and the paper with the rod, and just describe what we see. We wanna ask ourselves, does the rod behave more like a T tape or a B tape? Okay, and I have found that even better than just taking a rod like this, you can try it. Sometimes a PVC pipe does an even better job. So this is fur. I'm going to charge it up. Actually, before I do that, I'm going to reset the B and T tape because I think maybe their charge has worn off a little bit. I'm going to take this one off. Just reset these ones. B tape, T tape. See, they are really trying to attract. They're too close together there. All right. Okay. So I want to see, does the PVC behave more like a T or a B? So I can hear kind of the little static happening. I'll go to the foil first. That definitely attracts, right? Definitely attracts. Sometimes you get a little bit of a transfer there. Okay, so it attracts. So this is behaving, it's charged, right? Because it attracts both. Whether it's a B or T yet is still up in the air. clearly see that's repelling, right? It's repelling the B. That would imply like charge between this and the B tape. Let's see if it attracts the T. You can see that it's even better, right, than the tapes. I can get pretty far away and bring it in. Okay. So is this more like a B or a T? B, right? Because it's repelling B, but attracting T. Okay? So the next bit of information says, based on a number of observations, scientists assign the label of negative to rubber or plastic or PVC pipes. Okay? The fur or wool is positively charged, and the PVC or the rubber becomes negatively charged. And negative is associated with B. All right? So if we flip back to the front, it would be correct to say that our B tapes are negative and our T tapes are positive. So it would also be correct to say that positive charges would repel one another together, negative charges together would repel, a positive and a negative attract. So sometimes you hear opposites attract, opposite charges attract, like charges repel. So how do we explain it? Especially, how do we explain the fact that it didn't matter whether it was positive or negative, both of them attracted to the foil and paper? So the explanation is actually going to involve electrons and how electrons behave, okay? So you guys did some concept mapping last week. We knew that electrons are quite lightweight, and also electrons exist kind of on the outside of the atom. We've got the positive nucleus in the middle, and we've got these negative lightweight electrons that fill almost all the volume of the atom and are kind of on the exterior. Right? I'm going to move this up a little closer. So what I've done in your diagram is there's a little plus sign kind of in the middle of each circle. This is a very, very simplified version of an atom where the core is positive, and again, that core would be tiny. Remember, the nucleus is incredibly small compared to the size of the atom. But you can think of it as having kind of a positive core. The dots are going to represent electrons. They are negatively charged, okay? So I want to explain why the foil would attract to both the positive T tape and the negative B tape, okay? So we're going to add a little bit to the diagram. If we imagine this is kind of our strip of foil, like from side view, okay, even though it's thin, it would be many, many atoms thick. I want to imagine what happens. I'm going to draw a little line here. If I bring a positively charged thing near it. Okay, so imagine this is the positive T tape. And to start, it's got electrons that are kind of evenly distributed throughout the material. Electrons are negative. A negative thing is going to be attracted to a positive thing. So if I bring a positive tape over here, the negative electrons that are kind of evenly dispersed to start are going to be drawn towards the positive tape. And the thing about metals is that metals have at least one electron per atom that's loosely held. It can kind of flow around, okay? So I could imagine these 3 electrons kind of over here ending up on that side of the metal. So again, that's a hallmark of metals, is they have at least one electron that's loosely held. So they're gonna actually flow over towards one side of the foil. And again, this is like the thin side of the foil. And what they're gonna do is give that side of the foil a negative charge because they're all carrying their negative charge with them. The far side of the foil is now more positive than the near side. What happens when you get a positive near a negative? They attract, right? These are gonna come together. You can think of it like that. That positive tape is going to be drawn towards that negative side of the foil. So that explains the attraction. It has to do with these negative electrons flowing through the material. Now let's look at an entirely separate picture. We bring the negative tape over, or like the negative PVC pipe. This thing's negative. Again, to start, before I bring this negative thing over, the electrons are kind of evenly distributed. They're negatively charged, however. Negative charges would repel other negative charges, like charges repel. So what's going to happen here is those loose electrons are going to be kind of driven over to the other side. And now this is the side that's partially negative, leaving a positively charged side over here. Because some of their negative stuff has gone away. If my negative stuff goes away, now I'm positively charged, if I'm an atom. Again, we have the case where opposite charges are together, opposite charges attract, they're going to be drawn together. And again, the flow of electrons here is due to the fact that aluminum is a metal, and that is a characteristic of metals. Okay. The paper also did that. Okay, paper is not a metal. The electrons in paper do not flow around very easily. That's a hallmark of nonmetals. Nonmetals tend to hold on to their electrons. And therefore, we don't have these kind of loosely associated electrons that can flow around. But we still want to be able to explain why there was a weak attraction. So let's see if we can figure that out. So if I bring a positively charged T-tape over, this electron that was associated with this atom is going to be attracted to the positive charge. As will this one. It's going to be a little bit less attracted because it's a little bit further away. But these two electrons can't flow through the atoms. They can't flow across the material. So rather than having them kind of all randomly distributed, you can imagine that they do get kind of pulled towards the positive charge. But this electron is tied to this atom because it's a non-metallic atom. It can't flow over it into another atom space. So what tends to happen with paper is that it somewhat gets a positive or a negative charge over here, but it's not nearly as much. I'm going to draw a little tiny negative sign. So there is an attraction, but it's nowhere near as strong, okay? It's a weak attraction. But the negative tape also attracts the paper, so we want to make sure that we can explain that too. So if I bring a negative tape or negative PVC pipe over, it's very negative. Now the negative electrons are going to be pushed away, but they're not going to be able to flow very far. They're going to be still kind of associated with each atom. So, yeah, this side ends up being a little bit more negative than the other side. It's not as strong of an effect. And this side does partially very weakly become positive, and so we see a weaker attraction with the paper. They're drawn together, but not with the same degree of force. Okay. So this idea of metallic atoms having at least an electron, one electron per atom that can flow, crucially important to the rest of the year, things that we'll do. Metals behave and react differently because of that. Non-metal atoms, you can kind of push the electrons around, but not so much, okay? All right, so a couple of other things I want to show you related to this, kind of little tricks that you can demonstrate with this idea. Back up again a little bit. Get the desktop here. Okay. So this is kind of an interesting trick that you can use the idea that this PVC pipe can become negative. Oh, here it is. It's right in front of my face. So aluminum pop can. I can make the PVC negative. What actually makes it negative is electrons are rubbing off of the fur and being transferred over to the PVC. And then because the PVC is a non-metal, those extra electrons are kind of stuck, okay? So this should attract, it would have attracted foil, right? It also attracts paper, not quite as strongly. So it should attract the aluminum in the can. So I should be able to make use of that by getting it to roll without even touching it. It's always going to attract, so if I bring it close and kind of keep it the right distance away, I can get it to roll around just from that attraction. Okay, and the cool thing about this effect is it happens over empty space. They don't have to be touching like a lot of forces. A lot of things, if you want to put a force on something, you have to physically touch it. Electric charges don't work that way. And it turns out, the closer you get, the bigger the pull is between those opposite charges. Okay. This also works with water for kind of a different reason. I want to show you guys this. Might have to turn it on. Just want to make a thin stream of water. Turn on the wrong one. Charged up negatively. Get this out of the way. I don't know how well you can see it from where here. You get the stream of water to actually bend towards PVC. It's not happening as strongly as it does sometimes. Make it thinner. Yeah, there we go. You can really see it pull towards. And that's because water molecules, as we'll learn this year, have a negative end and a positive end. There we go. So it's easiest to explain in a diagram. So water molecule, H2O, right? We've got an oxygen atom and 2 hydrogen atoms. So when we get into bonding and talk about covalent bonding, we actually are within the molecule sharing some electrons between the oxygen atom and the hydrogen. One of the characteristics of oxygen is that it has a very good ability to draw in electrons. So even though they share some electrons, the oxygen kind of wins a tug of war and has kind of more access to the shared electrons. So a water molecule actually picks up a partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. It's not a full transfer of an electron, but it does result in what we call a polar molecule. It has a negative end and a positive end. So if I put that together, so if I have a stream of water with a bunch of these, flowing down in stream, falling, okay? Ordinarily, they would be kind of randomly oriented. They wouldn't necessarily be in any set kind of organized way. But if I bring that PVC pipe over here, it's like a big negative charge. And again, what's going to happen with negative charges? Well, this water molecule, its negative end is going to repel away from that negative charge of the PVC, and it's going to become kind of oriented in space like that. Same thing here. That negative charge, when it flows past the pipe, is going to flip. Same thing here. The positive side ends up towards the PVC pipe and they're drawn together. So that's how you're deflecting that beam of water towards the PVC pipe. The water molecules orient them in such a way that the positive end is closer and you'll get an attraction. So there are a lot of other cool things you can do with this. I'm going to hold off on any more demonstrations today. Stop.